Hello everyone, I am Shikhara and today I will be talking about vocal sequences in frogs and how they change with behavioral context. This presentation is part of the DAB Best Student Presentations for SICB Plus 2022. Many animals communicate with each other acoustically. In tetrapods, acoustic communication is seen in all four major extant clades and is vital to reproductive and social systems of many animals. Birds and mammals in particular have proved to be a rich source of acoustic complexity, and several forms of combinatoriality and context-dependent vocal syntax have been studied in these two groups. Other animal taxa, however, remain relatively unstudied. Anurans are a diverse amphibian order that use vocal signals to convey information about location, territory, body size, reproductive state, and mate quality. The life history of frogs and toads thus strongly requires efficient mechanisms to convey complex messages, often to diverse receivers, through acoustic communication. As such, anurans provide a good model system to study the evolution of vocal communication and syntax in vertebrates. To this end, we studied the vocal behavior of Nyctibatrachus humayuni and Pseudophylotis amboli, two distantly related endemic frogs in the Western Ghats rainforest of India. Using observational field studies spread across two field seasons and two states, we tried to tease apart the relationship between vocal sequences and behavioral context in these two species. We sampled vocalizing frogs in three different behavioral contexts. Frogs could either be vocalizing alone, vocalizing in the vicinity of vocal conspecifics, or be engaged in territorial disputes, which involved aggressive posturing and physical contact. We asked whether note usage and vocal sequence structure changed across behavioral contexts. In the case of N. humayuni, only a single case of a territorial dispute was observed, and thus we only compared vocal behavior across two contexts. The two species we studied both had multi-note repertoires, but differed in vocal repertoire size. In each of the figures shown here, the upper plot is an oscillogram in which the y-axis represents amplitude and the x-axis represents time. The lower plot is a spectrogram, in which the y-axis represents sound frequency, the x-axis represents time, and darker colors correspond to higher energies being allocated to the respective frequencies. N. humayuni, whose repertoire is shown on the left, had a small repertoire consisting of just two note types, an ascending note, or AN, and a descending note, or DN. N. humayuni could either emit a single AN or could choose to append anywhere from 1 to 7 DNs to the end of an AN. P. amboli, on the other hand, had a relatively large repertoire consisting of 6 different note types. You can hear each of these note types for yourself by downloading the supplementary video provided in the file section of the presentation. So what did we find? For starters, N. humayuni appended more DNs to an AN in the presence of vocal neighbors. In most cases, this was accomplished by appending a single DN to the call. In contrast, P. amboli used different note types in different contexts. Note types 1, 2, and 3 were primarily used when vocalizing alone or with neighbors, and note types 4 and 5 were used in territorial disputes. Furthermore, males vocalizing with neighbors emitted a lower proportion of type 2 notes and a higher proportion of type 3 notes than those that were vocalizing alone. In both cases, notes were not emitted in isolation, but were instead combined into sequences of note types. Here's a sample vocal sequence from P. amboli illustrating this. To examine how the complexity of these vocal sequences may vary between contexts, we measured the Shannon entropy of these sequences between behavioral contexts. The Shannon entropy of a stochastic process is a measure of its unpredictability and is commonly used as a proxy for the complexity of a process. In our case, a higher Shannon entropy indicates that a vocal sequence is more unpredictable or has a higher diversity of notes. Concurrent with our earlier finding that N. Humayuni appends more DNs in the presence of vocal neighbors, we found that the Shannon entropy of N. Humayuni vocalizations increases in the presence of a vocal conspecific. In contrast, the Shannon entropy of P. amboli remains unchanged between males vocalizing alone versus with a neighbor, but decreases during territorial disputes, suggesting that the vocal sequences employed during territorial disputes were more stereotyped in this species. We next modeled vocal sequences in both species as first-order Markov chains to examine whether transition probabilities between notes changes between contexts. The transition probability between note A and note B is the probability of emitting note B given that the frog has just emitted note A, and thus changes in transition probabilities reflect changes in the arrangement of vocal elements, which in turn are indicative of changes in sequence structure. In the plot shown here, arrows and the numbers annotated beside each arrow indicate transition probabilities, and the thickness of each arrow is proportional to the probability. Probabilities less than 0.1 have been omitted for the sake of clarity. Each node here represents a node type, and the size of the node is proportional to the average relative proportion of that node type present in the vocal sequence. To account for information representing silent periods between notes, we also included a node type 0, which is representative of silence of duration equal to 5 times the duration of the longest note present in that species. This allowed us to visualize how silence is distributed in sequences, letting us efficiently determine the start and end states of vocal sequences. In the case of N. Humayuni, we found that the AN to DN transition probability roughly doubled in the presence of a vocal neighbor, and the DN-DN probability also increased, both of which are indicative of more elaborate sequences. The transition probability diagram of P. amboli is more complicated. When vocalizing alone or in the presence of a neighbor, the most common note types are note types 1, 2, and 3. In both cases, inter-note transition probabilities are high, indicative of relatively rich sequences consisting of different note types. This is especially evident in the case where a male is vocalizing with neighbors. In stark contrast to this, during territorial disputes, most note types emitted are types 4 and 5, and inter-note transition probabilities are low even when present. Thus, in this case, most sequences were repetitive and stereotyped, consisting of a single note type being repeated for long periods of time. In both species, transition probabilities were significantly different across contexts, as was confirmed by a statistical test specifically designed for Markov chains. Thus, both species modified their vocal sequences based on behavioral context. However, not all animal sequences are Markovian. In particular, Kirschenbaum et al. Showed in 2014 that a wide variety of animal vocal sequences did not follow Markovian dynamics, and thus, modeling vocal sequences as a Markov process may not always be accurate. To account for this possibility, we came up with a novel computational approach to look for patterns in vocal sequences that is free of assumptions regarding the underlying stochastic process responsible for generating observed vocal sequences. In particular, this analysis is very generally applicable and did not require any assumptions about whether the sequences are Markovian. This allowed us to verify whether our earlier inference, obtained using transition probabilities, was sensitive to assumptions about Markovianity. Our approach, which we call co-occurrence analysis, measures whether two note types were more likely to occur close to each other than expected by chance alone. Let dCij denote the probability that note type j occurs within d-1 notes after note type I. Using a Monte Carlo algorithm, dCij can easily be obtained for a set of sequences. We now ask whether this value of dCij is more or less than would be expected by chance alone. To do this, we generated random datasets in which note types were randomly arranged into sequences with the probability of occurrence of each note type being equal to its proportion of occurrence in the original dataset. This allows us to compute an expected dCij if note types were to be arranged at random. By comparing the observed with the expected dCij, we can infer whether two note types occur more often than expected by chance alone. A value of drij less than 1 would mean that j co-occurs with I less frequently than expected by chance alone, and a value greater than 1 indicates that j co-occurs with I more frequently than expected by chance alone. We can now arrange all these drij values into a matrix to examine all pairwise co-occurrences between nodes. When applied to R frogs, co-occurrence analysis confirmed earlier findings and also highlighted some general patterns. In these plots, the drij matrix is arranged into a heat map, and redder values here indicate a higher value of drij. Specifically, redder values indicate that drij is greater than 1. Here, for example, we see that ANs rarely co-occur with themselves, instead co-occurring with either silence or DNs. In the case of P. amboli, co-occurrence analysis revealed the presence of groups of nodes that were very likely to co-occur with each other. For example, node types 1, 2, and 3 form a node group, and node types 4 and 5 also form a node group. These matrices also reaffirm earlier findings about stereotypy in territorial contexts, since both node types 4 and 5 are much more likely to co-occur with themselves, indicating that the two node types used in territorial disputes are both emitted in long, repetitive bouts. To summarize, we provide evidence from observational studies that frogs from two different lineages with different vocal repertoires both modify vocal sequences according to behavioral context. N. humayuni, with a smaller repertoire, uses more complex, elaborate sequences in the presence of vocal neighbors, whereas P. amboli, with a larger repertoire, uses different note types in different contexts. Various different techniques corroborate these findings. We also introduce co-occurrence analysis, a novel analytic technique for looking for non-random patterns in vocal sequences free of assumptions about the underlying processes responsible for generating these sequences. To see an application of co-occurrence analysis in analyzing syntactic structure in songbirds, check out my colleague Abhinav's talk in session 46, titled Allopatric Speciation and Syntactic Structure in the Song of Wren Warblers. None of this work would have been possible without my co-authors. Varun and I collected the N. humayuni data during a summer internship under Dr. Anand Krishnan in my first year of college. The P. amboli work was done with Anand and Dr. Seshadri K.S., who is at the Indian Institute of Science. This work has now been accepted as a paper in animal behavior, and corrected proofs are currently online. The code for all analyses, including the co-occurrence analysis, is present on a public GitHub repository. This repository also has a Jupyter notebook explaining how co-occurrence analysis works and showing an application of this analysis in finding commonly repeated residue pairs in amino acid sequences. Finally, if you have any questions, want a copy of the full text, or just want to chat, feel free to contact me on any of these platforms, and thank you for listening.